Hello and welcome back to Differential Equations. The goal for today is to learn about transformations of initial value problem. And that one is where we actually transform our differential equation using Laplace transform into algebraic equation. And when you have it as algebraic equation, you solve it using basic algebra, elementary algebra, whatever you want to call it, and then we transform it back to get the solution. So in general, what we have is, and I hope you already learned last time's lecture, right? Monday's lecture, because today we're going to use tables to do these transformations. So the differential equation problem, which is ax double prime, right, that's a function of t, plus bx prime of t plus cx of t equals f of t, with x of 0 equals x0, which is initial value, and x prime of 0 equal x prime 0. This is technically x of 0 equals 3, let's say, and stuff like that. You've seen that before. We'll transform into a Laplace transform of x double prime of t plus b Laplace transform of x prime of t plus c Laplace transform of x of t equals the Laplace transform of f of t. So this is our basic, this is what we are trying to achieve, and in order for us to do this, right, we have to figure out how to transform derivatives. We know how to transform a function. What we don't know yet is how to transform first and second derivative, maybe third, maybe seventh derivative, right? So we would like to learn the way to transform those. So we have to write the theorem first, and this is the one that you will be using. We'll also write we'll write two theorems. The first theorem is transforming the first derivative, and the second one is for any derivative. You will just have to follow the formula. So let's start with the theorem. I'll just say first derivative only, and then the next theorem will have all of them. So suppose that f of t is continuous and piecewise smooth for t larger than 0, and is of exponential order as t goes to positive infinity, so that there exists non-negative constant m, or constants mc and capital T, such that the f of t is bounded by this m e c t for t larger than t. There we go. So these are the conditions that need to be satisfied on the forcing function t, which means it has to be bounded by exponential growth. You can't have a function that grows faster than exponential. Those are the details that, again, would be going for the honors course and so on. You are required to know the formula. Then Laplace of the function f of t, the derivative of it, exists for all s larger than c. And here is the formula. Laplace of the derivative is equal to s times Laplace of the function minus f of 0. You can also write that as Laplace of f of prime of t is equal to s fs minus f of 0. You can write it in any of these two forms. Doesn't matter which one you want. Now the proof of this is fairly simple, right? To derive this, you can take the Laplace of some random derivative function, right, which is 0 to infinity of e to the negative st times f prime of t dt. We will use our good old u equals e to the negative st dv equals f prime of t dt. When you differentiate, you get du equals e to the negative st, negative s in front, sorry. So negative s e to the negative st dt, and for v you just have f of t because you are integrating, and when you integrate f prime you get your f back, right? So now when you put the formula together for integration by parts, you get that the Laplace of f prime of t is given by f of t e to the negative st 0 to infinity minus, well, there's supposed to be a limit and whatever, minus plus s times the integral of e to the negative st times f of t dt. So when you plug in infinity, it goes to 0. When you plug in 0, you just get f of 0, right? So this piece becomes 0 minus f of 0, and then over here plus s times, and this whole thing is your f of s. So f of s, and when you rearrange this, you get f of s minus f of 0. This f of 0 is your initial condition. Which is why you cannot transform these problems without initial condition. So you absolutely must have that. So now you can go ahead and chain these for the second, third, fourth derivative, and eventually you run into the theorem for any derivative. Because you can keep doing this, one by one for the transformations and plug one into another, and theorem for all derivatives when we skip all of the formalities they're important obviously as conditions, but you have to, so this is now nth derivative. You have to satisfy all the conditions in order for this to work. So I have the Laplace transform, and that's going to be s to the power of n Laplace transform of f of t minus Sn minus 1 times f of 0. So you already see your first derivative. This is if n is equal to 1, right? This will go to s to the 0, which is equal to 1, and you will get your first derivative formula if n is equal to 1. But if n is equal to 2, which is the second derivative, then this becomes s squared, and then you go through all of these. So then we have minus s, and then n minus 2 is the next one, but now it's f prime of 0, and then it goes that way all the way until you run out of powers. So we can write the Laplace of any derivative as s to the n fs minus Sn minus 1 of f of 0 minus Sn minus 2 of f prime of 0 minus minus sf to the n minus 2 of 0, and finally minus f n minus 1 of 0. This is the formula that will allow us to transform any differential equation, as long as we have initial conditions, into using Laplace into a basic algebraic equation. Let's have this thing at work. So you all know, hopefully by now, how to solve, let's say, a system y double prime, y prime minus 6y equal to 0, with initial conditions y of 0 equals to 2 and y prime of 0 equals to negative 1. So what have you learned in chapter 2? You learned in chapter 2 that you can transform this into characteristic equation r squared minus r minus 6 equal to 0. Then you are supposed to factor this and get r minus 3 r plus 2 equal to 0. You get r is 3, r is negative 2, and then that gives you the solution of y of t equals to c1 e to the 3t plus c2 e to the negative 2t. And then you use these conditions in a derivative, so we find a y prime of t, which will be 3c1 e to the 3t plus minus 2c2 e to the negative 2t, and now we plug the conditions in, right? So this is all chapter 2 over here. And you get to solve this and get the general solution that way, right? But we are going to also do this using Laplace, which is utilizing the formula above. So when you take a look at this now, you plug in your y of t is 2, and then 0, this is just c1 plus c2, and for the second one is negative 1 is equal to 3c1 minus 2c2. So this one times 2, and then add, I will get 4 is equal to 2 plus 3 is, no, 4, and then minus 1 is 3. Because I'm adding at the same time. And now I have 2. Yeah, so times 2, right? So that cancels C2. So C1, that's 2 plus 3 is 5 C1s. So I get that the C1 is equal to 3/5. And if that's equal to 3/5, then the other one is 7/5. C2 is 7/5, right? Because they need to add to 2. 7 plus 3 is 10, divided by 5 is 2. C1, that's a 9. Minus 14 is negative 5, divided by 5, good. So we get our general solution y of t to be C1, that's 3/5, e to the 3t, plus 7/5 e to the 2t, negative 2t. So all you see over here was your chapter 2 way to solve the problem. And we have the solution, right? That's our answer for a problem. So we can solve this problem, right? But the trick is, to use Laplace. And Laplace is going to use the formula that the Laplace of the second derivative, we can put y, let's put y double prime to match it, is going to be s squared f of s minus s f of 0 minus f prime of 0. So this is the transformation for the second derivative. And we also have Laplace transform of the first derivative, which was s f of s minus f of 0. And we have the Laplace of y, which is just fs. That's what we did last class. So these are the 3 formulas that we are going to use to transform our problem. So now, what is my problem? My problem was y double prime minus y prime minus 6y equal to 0. Let's go. Instead of y double prime, I have s squared f of s minus s f of 0 minus f prime of 0. Minus, now what's my y prime? Is s f of s minus f of 0. Then minus 6 times f of s equal to transformation of 0 is 0. So these are my transformations. And now I am supposed to plug in all of the values that we have. We also have that f of 0 is equal to 2 and f prime of 0 is equal to negative 1. So now we plug everything in. I have s squared f of s minus s times f of 0 is 2 minus negative 1 minus s f of s plus f of 0 is 2 minus 6 f of s equals to 0. So all I did is I changed for every f of 0 I placed 2 because that's what f of 0 is. And for every f prime of 0, I placed negative 1. So all I did is I plugged in these values. This gives us a basic algebraic equation, as you can see, that we can solve for unknown f of s. So now clean this up a little bit more. S squared f of s minus 2s plus 1 minus s f of s plus 2 minus 6 f of s equal to 0. So now let's put all of the f's in front. We have s squared f of s minus s f of s minus 6 f of s. And then we have the rest of this, which is minus 2s. And then plus 3 equal to 0. Because this 1 and this 2 create 3. And when I make a mistake, just let me know in the comments. So factor out f of s. So f of s, and then what's left is s squared minus s minus 6. Ooh, that is so familiar. Right? Look at that. Kind of reminds you of a characteristic equation. Now you can just skip to that step because you don't know what this is going to work out, right? Because you have all of these guys floating about, plus all of the negative signs and everything else. So you can't just jump all the way there. But it's a good checkpoint, right? And now, shove this to the other side, becomes 2s minus 3 when you move it. And we are left with, hey, f of s, which is transformation of the unknown f of t function, or I mean y, in this case, y of t. Your unknown transformation is 2s minus 3 over s squared minus s minus 6. So we need to solve for fs, right? That's algebra. And now we have fs equals everything else. Now use inverse Laplace to get y of t. So this is it, believe it or not. And this is why it's one of the favorite methods for all of the engineers, right? You take a look at the differential equation, you transform it into this algebraic equation. You know, if you were to replace this for capital X, you know, then you know to solve for X. So you're solving a basic algebraic equation. And now we are supposed to apply inverse Laplace to f of s, which would be inverse Laplace for 2s minus 3 divided by s squared minus s minus 6. This over here gives you y of t, and the other side, hey, it's partial fraction decomposition, and then using the chart for inverse Laplace. I mean, Laplace transforms really backwards for inverse Laplace. So it's inverse Laplace of, and now you have your a over s minus 3 plus b over s plus 2, right? Because the denominator over here factors into s minus 3, s plus 2, and we can do our partial fraction decomposition. So now you do your partial fractions. So that's as plus 2a plus bs minus 3b equals to 2s minus 3. You have your a plus b equals to 2, and your 2a minus 3b equals to negative 3. multiply top equation by 3 and add equations. Doesn't matter what you do, it's just get them anyway, get them done either way. That's going to give you 5a. B's are gone. 6 minus 3 is 3. And here is your a equals to 3/5. We remember 3/5 from before. And that means that your b has to be, in order for them to add to 2, 7/5. We remember both of these numbers. They were there. So now my y of t is equal to inverse Laplace of 3/5 times 1 over s minus 3 plus 7/5 of 1 over s plus 2. Now, what do we know from our inverse Laplace chart? If you look at the inverse Laplace chart, you find that 1 over s plus a transforms into EAT, right? That's the front of the book. Sorry, AE minus s minus a. Yeah, s minus a. So if you look at the front of the book, that's what you get. So y of t is 3/5. And now inverse Laplace of this, your a is 3. So e to the 3t plus 7/5 e to the negative 2t. There it is. So that's the same as the answer we had here. Now, true that the other method was faster, right? Less algebra, we had to deal with these things. But I'm just going to drop in one concept here. I'm going to get closer. Undetermined coefficients. Remember that horror? Remember the problem we did for what, 3 hours? I did that problem maybe 4 times, and you still had to help me to catch for that undetermined coefficients. You can go back and find where that problem was. Remember that horror? Yeah, Laplace is going to make a joke out of that, because you transform your problem and then in the end you are solving algebraic equation. So this eliminates undetermined coefficients and variation of parameters, integration formula, and all of that stuff is just gone. And you are using this one method which transforms, and then you will just have to go through the horror of partial fraction decomposition at the end to do the inverse Laplace. But apart from that, you know, it is a very structured, and it's always the same, and you use the chart and you really don't have to do any calculus. This reduced our problem to solving simple problems of in algebra. And that's I don't know, I think it's really cool. If you don't think it's cool, then you're in not just the wrong class, you're in the wrong life, all right? Because this needs to be insanely cool if you are taking courses that require differential equations. Anyway, so what else can we do, right? Well, we can do a whole bunch of stuff with the trig, with forcing, with those mass spring systems. And you can transform literally anything and everything and solve these transformations to get the problems. Let's take a look at this is much longer lecture. I want to take a look at one problem from homework that contains trig. I know they did 2 problems in examples, but let's let's leave those you can read, right? I'll just going to work out one of these examples from homework. Let's see what has trig in it. Problems 6 and 7 have trig. Problem 7 has a 3t, so that looks good. And see, now I don't care if undetermined coefficients or all of that. So I will just plow through the whole thing. Problem number 7 has x double prime plus x equals to cosine 3t. They say that x of 0 is equal to 1 and x prime of 0 is equal to 0. All right. We don't have the prime in this case. We have the double prime only. Now I noticed that the book likes to use capital X for transformation of x and the capital Y for transformation of y and capital F for transformation of f. That's good to follow when you have multiple functions, like you have linear systems and you get equation for x and equation for y. Yeah, then follow it. But if you just have x, just have y, then you can just use f's if you want to. The reason why I don't like using x is because you can confuse, if you are sloppy, and most of you are when you take the notes, right? You're not going to take the time to write every capital X like that, right? To make sure that it's different than when you write the simple x. Simple lowercase x that you're used to the variables. So these are the lower cases, these are the upper cases, but then they have these little lines on top. And writing it without the lines, it just becomes this versus this. And then, as I said, how good are you in taking notes? So I'm just going to go back and use f's because I'm a boss. So s squared f of s minus s f of 0, in this case x0, minus x prime of 0. So that's our transformation for the second derivative, right? So your powers of s will go down, so 2, 1, 0, right? And then you start using x and then x prime and then x double prime and so on. So it's very structured. So it doesn't matter what derivative you get, it's like that. We don't have the first derivative, so just plus f of s at the end over here. And now I need to transform cosine 3t. Now cosine 3t is our good friend of s over s squared plus 9. So one of them will have 3 and one of them will have cosine. Cosine has s. Good, I remembered it. And it's a plus. Hyperbolics are minus. Good. Wow. Still remember all of this. I pretty much memorized the whole chart. All right. So now plug in 1 and 0. So we have s squared f of s minus s. And then this one is 0. So this thingy over here is 1. And this thingy over here is 0 because of these two puppies right there. So plus f of s equals s over s squared plus 9. So now I have my f of s factored out, and times s squared minus plus 1. So s squared plus 1 goes there. And this minus s goes to the other side as plus s. So this goes to the other side, becomes plus s, and when I factor out f of s, I get s squared plus 1. Good. So now we get a huge mess on the other side, but we're just using algebra to solve that, right? To resolve the issue. So now you have your s squared plus 9 plus s divided by s squared plus 1. And technically, we are done with solving our differential equation because we solved for f of s. We just, if you take the inverse Laplace of this, you're getting your x of t. So we're good to go, right? The issue is the other side, right? So the way we're going to deal with the other side is we are going to multiply through by 1 over s squared plus 1 everywhere. Maybe I should make this orange or something. There we go. So if we go away, there we go. If we multiply like this, then we lose the double fraction. So now you have your f of s is equal to, and you get your s over s squared plus 9 times s squared plus 1 plus s over s squared plus 1. That's when you multiply the top, and on the bottom they just cancel, which is why we multiplied like this to deal. Wouldn't it be minus fs? Would it be minus fs? No, it's a plus fs in the problem, unless I copied the problem wrong. Problem number 7. It's a plus. It's a plus in the problem, so it's a plus there. And a transformation of x is just fs. The minus signs are for these when you do it. And when you are dealing with this, this is your x double prime plus x. Cool. So you have to follow the sign that it's given inside the problem. All right, cool. So this part is easy, right? That's just cosine of t. That's all it is, because it is s over s squared plus 1 squared, right? So that's easy. So we don't have to worry about that one. We have to sweat over here because we have the partial fraction decomposition to deal with, let's deal with the partial fraction decomposition on this part here. That's as plus b over s squared plus 9 plus cs plus d over s squared plus 1. These are unfactorable quadratics. Now, again, I did tell you yesterday, on Monday, go back to Calc 2 and relearn your partial fraction decomposition, right? Because if you learned it for a grade in Calc 2, obviously, now that you need it, you have to relearn it again if you want this grade. Those of you who learned it to know it, you just apply it real quick, and we go from there. All of this is going to be equal to s parenthesis times parenthesis. So cross multiply everything for the common denominator. That's going to be as cubed plus bs squared plus as plus b plus cs cubed plus ds squared plus 9cs plus 9d equals to s. Awesome. We have equation for s cubed, equation for s squared, equation for x, and equation for constant. S cubes, a plus c equal to 0. There are no cubes on this side. Squared equation, b plus d equals to 0, because there are no d's. There are no s squares on the other side. And s, that's A and 9C is going to equal to 1. And finally, constant B plus D equal to 0. B plus D equal to 0. So B plus D equal to 0, that's going to give us a 0 there, because 0 plus 0. I don't like it. Did I lose any term? 1, 2, 3, 4, 5, 6, 7, 8. All right, so when I subtract these two equations, A minus A is 0, 9 minus C is going to give me 8C equals to 1, C equals to 1 over 8, and that means that A is negative 1 over 8 because they have to add to 0. So my Fs is given by negative 1 over 8 B0. So I have S over S squared plus 9 plus 1 over 8 plus 1 over 8 C survives, so S over S squared plus 1, and I still have plus S over S squared plus 1 over here. Yep. Now we're going to write this one more time. Notice that these are the same. So that's going to be 9/8 S over S squared plus 1, and then minus 1 over 8 S over S squared plus 9. So I wrote this first when I added, and then put the second one, put the first one second because the negative 1 over 8, so it's nicer. There we go. And now we use the inverse Laplace. So we're going to take the whole expression over here and hit it with the inverse Laplace. So that's going to give me x of t, and then 9 over 8 cosine t minus 1 over 8 cosine 3t. The coefficients are there, everything is there, we're done. Why is it cosine? Because s over s squared plus k squared transforms into cosine kt, and your coefficients in front stay the same, does the signs stay the same, all of that stuff. Would A be 9 over 8? I don't know, would it? When I subtract these two equations, I have A minus A is 0, 9C minus C is 8C, 1 minus 0 is 1, that's good. So C is 1 over 8. So I have 1 over 8 plus C equal to 0. C must be negative 1 over 8. I mean, A, what did I do? Oh, C is 1 over 8. So A plus 1 over 8. The A must be negative 1 over 8 in order for them to add to 0 from the first equation. And if you check that in the second equation, you get A, which is negative 1 over 8, plus 9 over 8 is 8 over 8. It's good. All good. All good. Yeah, C is negative. Yeah, it's good. Negative 1 over 8 plus 9 times 1 over 8 is negative 1 over 8 plus 9 over 8, which is 8 over 8, which is 1, which is 1. It's good. Rewind. Rewind the video for additional fractions. All right, cool. We got it. There it is. There it is, the problem. So what else is in this section? We are not done. We are not done, my friends. Over here we'll have to enjoy more. Ooh, solve the system. Yeah, everything that we did so far transforms into these. So let's see. So solve the system. So they gave us the system of these spring mass. So you have a mass M1, have a mass M2. There it is. There it is. Displacement for X, displacement for Y. And this mass is given as 2, this mass is given as 1, this spring constant is 4, this spring constant is 2. And they are going to bother the system with a wave function like this, just to be extra annoying, right? So when you have a system like this, we know what to do in terms of the setup, right? Because we had that equation where we learned that the spring, x minus y, and in these cases here, and you have the spring constant k. We don't have a dash pod, so there will be no first derivative, right? At least that. So we use the same method of transforming this. So for each mass, you write the system. So mass on the first one is 2, and that one is going to be negative 6x plus 2y. Now we used, if you remember, we used x1 and x2, and now we're using x and a y. So I'll just say old x1 is now equal to x, and old x2 is now equal to y. If you are going back to your notes to really learn this, because let's say you want to be mechanical engineer and not work the sales, but you actually want to design things, then you need to figure this out. And the x and a y we used to call x1 and x2. I don't remember. It was chapter 4 or chapter 3, or it was somewhere, right, whenever we did it. And we have our second equation here, which is for the second mass, right? So the mass is 1, so 1 times y, the displacements, is going to be 2x minus 2y plus, and now we have our 40 sine 3t. That's our forcing term. So you are yanking it, right, with a frequency 3 and so on. All right, cool. So now we have our differential equation, and we are going to initial conditions. X of 0 is equal to x prime of, they're all zeros. Wow. Well, that's going to help a lot. All right. So everything was in the equilibrium, So you have your positions in the equilibrium, and initial velocity was also 0. So position and the velocity were all 0, and then you apply this yanking force here that sets the whole thing in motion. And now with x and y of t, you are tracing the positions of these masses in time. Cool. Well, let's transform these systems. Now, because of this, all of those f of 0 and f prime of 0 and all of that stuff, that's all zeros. So we can just transform the equations. And now, since we have x and a y, I can't use f of s anymore. I have to use capital X's. Now, the beauty of this is once I transform this system, it will transform into a system of algebraic equations, you know, two variables, two unknown, and all that stuff. And then we deal with that rather than dealing with the system, with substitutions and everything else. So let's go and transform. What do I have? I have 2s squared f of s, and then I'll just put minus 0 because those are the transformations. Is, oh, I can't use f. I just said that. I have to use x. Is equal to minus 6x of s. Well, actually, I don't have to write the little bars because I put of s. Okay. Plus, hit the shift, plus 2y of s. There we go. And then s squared y of s minus 0 is equal to 2x of s minus 2y of s plus 40 times, and now this is the one where you actually put the k on top, so this is 3 over s squared plus 9. Now it's good to put this line every time you deal with the two equations with two unknowns. So we have 2s squared x of s is equal to negative 6x of s plus 2y of s. I'm just going to make it look clean. And then s squared y of s is equal to 2x of s minus 2y of s plus 120 over s squared plus 9. All right. So now I have my system. And this system is, as you can see, just a system in terms of x and y. So let's put everything on the left side and everything that doesn't have x and a y on the right side, and see where we get from there. Oh. Battery Aziz, let's go. There we go. All right. So what do I have? Give me a second. All my systems are falling apart this morning. Come on. There we go. All right. So now I have my xs. Now let's just move everything. So 2s squared x of s plus 6x of s minus 2y of s is equal to 0. Minus 2x of s, right? Plus s squared y of s plus 2y of s is equal to 120 s squared plus 9. So we have 2s squared plus 6 of x of s minus 2y of s is equal to 0. And we have negative 2x of s plus s squared plus 2y of s is equal to 120 s squared plus 9. So I just need to solve for x of s and y of s in terms of all of the other mess. And that's very easy to achieve because I can divide the top equation by 2 and I will get s squared plus 3 x of s minus y of s equals 0, and the bottom equation I didn't touch at all, plus s squared plus 2y of s equal to 120 over s squared plus 9. Solve the system. Well, this one is a joke. Y of s is equal to s squared plus 3x of s, right? Just solve for ys and then plug in. We use a basic substitution. You can use elimination as well. And your matrix obviously won't work here because it's just a mess. So when I plug in for y of s, I get negative 2x of s plus s squared plus 2, and instead of y of s, I have s squared plus 3x of s equals to 120 s squared plus 9. So now everything is in terms of x of s. I still have to do the work. I have to FOIL, I have to subtract the 2, right? So when I factor out x of s, in parentheses over here I have s to the 4th plus 5s squared plus 6 minus 2 equals to 120 s squared plus 9. That's x of s, and then I have s to the 4th plus 5s squared plus 4, and that factors nicely. So this is where you go woohoo. Let me see that woohoo in a chat. 20,000 people watching, it's nice. All right. So now this one factors into s squared plus 4 and s squared plus 1 equals to 120 over s squared plus 9. And we got our excess. It is 120 divided by s squared plus 9, s squared plus 4, s squared plus 1. Now you're going to say, is this going to be a 6 constant partial fraction decomposition? Yes, it is. So 6 constant partial fraction decomposition goes here. This is going to be the rest of your day, I guess, to fill in the blanks. And that gives us our beautiful x of s as 5 over s squared plus 1 minus 8 over s squared plus 4 plus 3 over s squared plus 9. Right, so that's 30 minutes later. It's not 30 minutes. It's going to take you 7 to plow through that. And now I have XS, right? Because I can inverse Laplace this. So I hit this with the inverse Laplace, and I get my x of t, which is 5 sine t minus 8 sine 2t plus 3 sine 3t. All right, those are all the all of your k's. Oh no. No. These constants are wrong. This constant is 2. Lies. 4. Because your transformation is k over s squared plus k squared. Gives you sine kt. So from here, k is 1. So if k is 1, then the entire 5 stays as a front coefficient. Now for this term, your k is 2. So when you plug in k is 2, you get 2 over s squared plus 4. But you also have 8 up there. So there's a 4 times this mess to give you 8. So that's why this is a 4 there. And the last one is just a 3 over s squared plus 9. So the last one is good. All right, cool. Hey, we're done with the x. And now so now we do the y, because that was just x. We need to solve for y, and we have the function here for y. This one, right? So y of s was s squared plus 3. Was s squared plus 3? Yeah. Of x of s, which in our life is, all right, wait for the noise. So in our life, that's 120 s squared plus 3 divided by s squared plus 1, s squared plus 4, s squared plus 9. And now we redo the whole procedure. Now you can do that, or since you have what, easy tablet, relax. Thank you. Since you have these, where are they? Equations, you can get your y using this equation here, because your x, you know what your x is, and you can differentiate it twice to get the prime. So you can either, right, it's pick your poison, right? So I have to do this slowly because the tablet is already overheated. I don't know, it just gets jumpy. So again, partial fraction decomposition, or use, which should be way faster, use your equation 2x double prime is equal to negative 6x plus 2y. When you divide this by 2, you get that y is equal to x double prime plus 3x. So we already know that x is equal to mess. So x is equal to 5 sine t minus 4 sine 2t plus sine 3t. So you can just go ahead and find the second derivative of this. Now I'm going to do the second derivative in one shot. Derivative of sine is cosine, derivative of cosine is negative sine, so negative 5 sine t. Derivative of sine is cosine, spits 2 out, makes that into an 8, and then makes it into plus 16 sine 2t. And then this spits out a 3, and then another 3 makes it a 9, so it's a negative 9 sine 3t. And then you just plug in these two, and that will give you y. So y is equal to x double prime, which is minus 5 sine t, plus 16 sine 2t, minus 9 sine 3t, plus 3 times up there is 15 sine t, minus 12 sine 2t, plus 3 sine 3t. This is much faster than cranking another 6 variable fraction, partial fraction decomposition. And that gives us our yt. 10 sine t, 16 minus 2 is plus 4 sine 2t, minus 6 sine 3t. I really don't want to write this again. So your solution is here. And it's already particular solution, remember, because all the coefficients are calculated. You don't have the C1, 2, 3, and blah, blah, right? It's done. So everything done in one shot. And this was a problem where, remember your forcing term? What was the forcing term? The forcing term was a 3t, right? We have a 3t in the answer. This could have been the problem with undetermined coefficients within the system of equations. Holy nightmare. That would take forever to solve the regular way. So if this looks like a mess, it's nothing compared to what this would look like, right? I understand the first example was unnecessary. Sure, you don't bring the sledgehammer to hang a picture, right? But when you have a situation where you need a sledgehammer and you are going and chipping away with a regular framing hammer, it's not going to go really well. So Laplace is there to make a lot of these calculations that were really nasty before a little bit easier. So your job is to always have the Laplace transform table with you to recognize the inverse Laplace. Obviously practice that a lot. You can tattoo the chart of Laplace transforms. That would be a cool tattoo, right? Rather than the chicken fences and stuff you put, or the Japanese words or whatever, Chinese, whatever you now. Anyway, what else do we need to look at? Transformation of integrals. Okay. Oh, and then that ends the mess. Nice. Okay, so here is another theorem. So, transforms of integrals. Remember how I told you that some functions can only be written as they're defined as integrals? And I gave you the error function li, si, and so on. So we need to know how to transform those as well. So if f of t, the function f of t, is a piecewise continuous function, for t larger or equal than 0, and satisfies the condition of exponential order. Right, so f of t is going to be bounded. It's the same as before, MECT for t larger than t, then, and now we have the Laplace transform of the integral 0 to t of f of the tablet is overheating and it's very difficult to write now. F of tau d tau is going to give you 1 over s, the Laplace transform of f of t, which is just f of s over s, easily written. And the inverse Laplace of f of s over s is going to give you the integral. Now, what is this tau business? It's just a variable that it's because look, we're going to plug in a t to get the function f of t. Those of you who remember Calc 1, again, whether you studied to learn the Calc 1 or studied to learn to have the grade, right? There's a big difference. Integral, if you remember, there was the integral d dx, integral 0 to, or a, to x of f of t dt for the fundamental theorem of calculus. I don't know if you remember, so fundamental theorem of calculus, FTC. And when we integrated this, we get the derivative of the antiderivative, but the antiderivative would be in respect to t, and then we plug in 0 to x. And then we get, copy d dx, you get antiderivative in respect to x minus f derivative of 0. You can put a there. And now when you take the derivative, you just get f of x. And then the derivative of this is some number. F of 0 would be some number. F of a would be some number. So you would just get f of x back. So technically the formula says that the derivative and integral cancels each other out, right? And you are getting, but see, the trick is that we use the variable t as intermediate variable. Our main variable was variable x. So now what it tells me is that if I differentiate the integral of, I don't know, e to d, no, I don't want to use e to dx. If I differentiate, let's say this, I will just get that back, right? I will just get that because these guys cancel each other out. So now when we have the, so this was, going back to Calc 1, so you have seen these types of things. So if I have some kind of integral 0 to t of f of tau d tau, this is just a placeholder for the variable that will eventually be there, because when you integrate this, you will get the antiderivative. Oh, now we're using f for Laplace, and okay, I'll have to spell it out. F of tau 0 to t, and you get your f of t minus f of 0, and then you go. Now this is the antiderivative, not Laplace in this example here, because I'm just showing you that the variable tau is we call it a dummy variable as well. It's just like a placeholder for the variable that will actually be the main variable, because you see that once integrated, the function is in terms of t, because you had that t as a limit to plug in. So that's explaining this formula. So we have our formulas here, and now we can go ahead and transform some integrals and do Laplace transforms and whole bunch of other stuff. So let's see. Now this is obviously important, because once you do your partial fraction decomposition and so on, you might run into situations where you have to leave your problem in terms of the integral, and then you would integrate. I mean, not leave it in terms of integral, but then integrate that problem. I wish I could quickly find a problem that would fit this, but chances are slim just by staring at this. How about, let's see what problem 23 is going to bring. Find inverse Laplace for 1 over s squared minus 1. So whether it was a system of differential equations, which just have a single equation, it's just something, right? You had to go through all of these calculations, and once you solved for everything, right, you went through the whole procedure, and you are now here, right, where you have your x of s or y of s or something, right, is equal to that mess. What's happening? Well, we are supposed to do partial fraction decomposition and go from here. I just hope that this one gives us, yeah, whatever. Let's try. So what is my partial fraction decomposition? It's a over s plus b over s squared plus c over s minus 1 plus d over s plus 1. These are four linears. Oh, this one is a reducible quadratic. When it's a plus, is irreducible, right? The minus you can use difference of squares. So we have, so this one is a repeated linear, and then two more linears, basic linears, right? So two basic linears and a repeated linear. All right, cool. So what do I have? I just have to multiply this by a whole mess of things. I will be teaching this. I will be teaching this to my algebra class right after this class. So in 45 minutes from in 40 minutes, right? So in 40 minutes from now, I will be teaching this to my algebras. So if this makes no sense, just stay on. All right, just stay on for the next. All right. So what do I need? As I say to my algebra students, you already have your common denominator. let's play the game of what's missing. You're only multiply in each one of these terms what's missing. So s squared minus 1 is missing. And then over here is s squared minus 1 is missing. Over here is s plus 1 is missing. And over here is s minus 1 is missing. So now we multiply all of that out and we just set it equal to 1 because there's just equal to 1. So we have as cubed minus as when I multiply, right? Because what you multiply on the bottom, you multiply on top as well, right? So this is s times, that's how we know what to multiply. So s times s squared is s cubed times a, and then s times 1 times a. Over here we have s squared minus 1, so that's an easy one. That's bs squared minus b. Over here I have s plus 1, which is plus cs squared plus cs. And at the end I have s minus 1 to multiply, so that's ds squared minus ds equals to 1. We have s cubed, s squared, s and a constant. A equals to 0. Yeah, it was easy. Then I have a bs squared, cs squared, ds squared, so b plus c plus d equals to s. That's a 0. Then I have the s terms, which is minus a plus c minus d equals to 0 as well. And now I have the constant terms, which is just negative b, and that's equal to 1. Wow, this is a perfect exam question because it works out so well. So when we plug everything in, we have that a is equal to 0. We have that the b is equal to negative 1 so far. So when you plug all of those, if b is negative 1, then c plus d is equal to 1. And if a is 0, c minus d is equal to 0. You add these two equations, you get that the 2c is equal to 1, c is a half, and if c is a half, d is also a half because they have to add to 1. So we didn't have to use the integral thing. Oh well. So b over s squared negative 1 over s squared c over, so that's 1/2 over s minus 1, and the d over, so plus 1/2 s plus 1. Cool. So this is what our f of s equals to when we are done with the partial fractions. So now that we are done with partial fractions, I'm going to write this one more time to make sure that I have all of my constants away so they're not bothering the form of the question, right? So I need some room to put in that I'm going to do the inverse Laplace. So f of s is equal to negative 1 over s squared plus 1/2 1 over s minus 1 plus 1/2 1 over s plus 1. So this is my situation here for to set up for inverse Laplace. So what do I have? This is going to become f of t or x of t or y of t, whatever is in the problem. And then I have negative, and now I have s squared. Now 1 over s squared is just a t. That's, and then plus 1/2, and this becomes e to the t plus 1/2 e to the negative t. And you are all already done, right? Now, I'm going to flex a little bit, because we can also do f of t is equal to negative t plus e to the t plus e to the negative t over 2. And that gives us what? Exactly. Yep. Now, if you haven't seen that, over here we can have negative 1 over s squared plus 1/2 of 1 over s squared minus 1. Oh, hold on. No. You have to do the common denominator and all of that stuff. So it's not 1/2 there. When you do the common denominator, that's going to be, there is a 2 from those halves. That's going to be s plus 1 plus s minus 1. So now those cancel. So it becomes negative 1 over s squared plus 2, there it is, plus 2s over 2, s squared minus 1, then 2's canceled, and s over this, good. S over is the cosine hyperbolic. Ha! So there's that. And clearly this answer is way better than that one on top because it has less operations. Hashtag computer science over here, right? You want to compute less operations. If you want to compute less operations, then you have to have simplified answer every time. So we did not run into any of the integration. So there are a couple of derivation problems, couple of then they have some of these problems. They show you also the graphs of how the signals would work, and then that's it. 7.3 translation and a partial fraction. That's just moving things left and right. More application, that's going to be quick. So we're going to take a look now into, I'm going to restart the stream. This is going to be very quick on 7.3, translation and partial fractions, because we already did partial fractions and all that. It's just shifting. And then I'm going to open the first, so we're moving the exam a little bit. No, exam is supposed to be this weekend, right? So, no, not this weekend. I'm completely lost. way too many classes. I'm actually, for online teaching, I'm equivalent doing of 7 classes. And I should be doing only 3 calc classes. I'm actually equivalent now to 7 courses, the number of students that I have in the online courses. I have no clue where I am. So for you guys, we need to have exam 3, and exam 3 should be on as soon as possible, so that we have enough time to take a look also at, we need to cover 7374. We can stop there, even though there is some other cool stuff in Laplace, like impulse functions and so on, because we also need to do 2 sections. So I have to do 4 sections minimum. Oh, we actually have time. Okay. Let's just do the quick dates and so we are left with Friday, Monday, Wednesday, Friday. Let me just check. So Friday is the 1st, and then Monday is the 4th, and Wednesday is the 6th, and Friday is the 8th. And then we also have the Monday 11th, and the 5/12 is semester ends. So final is going to be Sunday through Tuesday, which is 5/10 through 5/12. So that's 3 days. We must have the final then, because the semester ends on the 12th and your summer one begins on the 18th. And then there is that week in between for us to do the syllabus and so on. So, post and set up for the classes and stuff like that. So, we must have that. So we can have the exam 3 anytime. I really don't care. Now, this is the final. So chapters 1 through 8, what we covered. So final is everything 1 through 8, what we covered. Exam 3 is sections 4 and 5. Now, there was a suggestion, because you have your chapters 7 and 8, which are not on any of the tests yet. we can have the cumulative final or exam 4 only on chapters 7 and 8. Now, you guys will have a choice what you want to take. Final will have 7 and 8 on it. Exam 4 will have 7 and 8 on it. And this is something that we have to, because the problem is that the department made the final optional in a voting, and because the final is optional, the students who opt out not to take the final, they will take exam 4. The students who want to take the final will not take exam 4. So this is how it goes. Options. We had our midterm, which was exam 1 plus 2. Everyone is taking exam 3. And then exam 4. And then average is placed into final. That's option 1. I'll have to post both tests. It's just mess. Option 2, midterm, exam 3, final, which is actually the syllabus. So, those of you, and you don't have to tell me which option, because on that last here, on the last Sunday, Tuesday, you will either take exam 4 or you will take the final. That's what you are going to do. Those of you going in with low grades, obviously final is better because it covers everything that you hopefully studied to improve. I mean, you will make your choice. So you take whatever option you want, and then once I have the grades posted on Canvas, you will choose the option of pass no credit or keep the letter grade. So letter grade is standard. If you don't make any choice, letter grade will remain. And all the F's will be converted to no credit. All of the D's are converted to no credit because you can't transfer it, and you can't, move on with the next, like partial differential equations with a D. So all of the F's and D's are converted into no credit automatically. And then for A, B, C's, I mean, probably everyone will keep their A, obviously. For a B and C, technically you are picking the option whether you want your grade B to show up on a transcript and be calculated in GPA, or you want your B to be not included and calculated. So all of this will be clearly spelled out in the announcement. Now, exam 3 on chapters 4 and 5 needs to happen sometimes. So the question is when. We can do, again, Sunday, Tuesday deal. We can do Sunday, Tuesday deal. And then the next week, Sunday, Tuesday, is the final or the, right? So let's do Sunday, Tuesday. That's actually spread out. So Sunday, Tuesday, which is 5-3 through 5-5. Okay, that's much better. Exam 3 on chapters 4 and 5. I'm going to put quiz right now. So exam 3 on chapter 4 and 5 is going to be 5-3 through 5-5. And then exam 4 or final. My tablet is exploding. Exam 4 or final will be 5-10 through 5-12. There we go. So if you pick exam 4, it's just 7 and 8. If you pick final, that's 1, 2, 3, 4, 5, 7, and 8. We did not have chance to do anything in chapter 6, unfortunately, but we lost a week. We lost 2 classes due to tech issues, and we lost 1 class because I had to leave because of my son, an emergency, if you remember. So we lost 5 classes, and those 5 classes would cover chapter 6. So I guess get that. All right, so next class, which is Friday, we are going to do a quick 7.3. That's going to take less than 30 minutes, plus review. And then we have 8.1, 8.2. Those are the important sections. Yes, 8.2. And then Friday is the review. And Monday also review. Oh no! Where's my 7.4? 7.4, 8.1, 8.2. There we go. This is terrible because you can take before the review, but Friday, well, we can have the review also on Friday. All right, so remember that there are no quizzes for final. So you only have quizzes for exam 3. And obviously, to make it fair, there will be no quizzes for exam 4 either. So we're not going to make it if you take exam 4, then you have quizzes. And so I'm going to go now and open your quizzes. So E1 exam 3, quiz 1 on 429. So just finish it today. Only 4 problems, as usual. And then E3 quiz 2 tomorrow. 4 problems and so on. No quiz for exam 4/final. So that's what it is. I'm actually now clicking on my MATLAB here. So we'll have time to finish the crucial stuff so you can survive. If you don't learn the Power Series Chapter 8, do yourself a favor and never sign up for partial differential equations. Never sign up for thermodynamics, some advanced chemistry, and material 400 level courses, because they're all going to use that. So just change the major at that point if you don't know how to deal with chapter 8, those two sections, because most of the work later on is going to be the power series. All right, so I have now 10 minutes. I have to post your quiz and then cool off these tablets to get ready for my next class that starts in 10 minutes. I will be back on Friday here, and for the Friday we're going to do the quick 7.3 and then the review, and then we'll go from there. Bye.